Okay, good day everyone. Assalamualaikum. So I'm going to repeat what I have taught you about example 6.2. So this is in topic 6, bending. So we go straight away into example 6.2. So we have this kind of beam. So I think I need to change the color. Maybe blue. Okay, we have a fixed end, and this is a cantilever because there's no support at the another end, and we have this triangular distributed load. Alright, so this is a fixed end. Maybe I don't have to, never mind. So the length, I need to change color, red. This length is L, the length of the beam, and we have W naught to be the highest load, which is at the end of the beam. Okay, so in this case we will need to examine the free body diagram FBD. Okay, I don't think that writing using red is right. Okay, FBD. So we can draw the beam, and then from the triangular distributed load, I call it triangular distributed load, we can represent it with one single load. So this is the load, and we represent it right here, which is 2/3 from the length. Okay, please understand why it is 2/3. If the distributed, let me draw. If it is like this, the distribution load is like this. Okay, so the 2/3 is right here, 2/3 from the end, or 1/3 from here. So let's say the length is L, so this length is 2/3 L, but in this case the length should be 1/3 L. Okay, so this is for your understanding, so I'm going to erase this. How to just to erase this. Okay, so we need to understand the free body diagram, what the forces involved and the moment as well involved in the structure. So this is actually pretty simple, not so many forces and moment involved in this structure. So we have a reaction force right there, so V1, and this one we call it P, and we have moment right there, and this we call it M1. Okay, from this free body diagram, so I think yes, that's all component that involved in the structure for the free body diagram. So we have W naught over there. Okay, since the shape of the distributed load is triangular, so we need to understand that anywhere, let's say this is X. I need to change the color, I think. Oh, this looks pencil. So this is X, and this is W. Okay, so W over X should be equal to W naught over L, which is L is the length right there. So we can get the equation for W, which is W naught X over L. Okay. So the value of W is changing with the value of X. Changing with X. Okay. So now that is free body diagram for the overall structure, but right now we want to investigate the free body diagram when we when we cut the beam at the middle. This is because we want to examine the shear force within the beam. So we cut the beam. Sorry, my color is not consistent, but hopefully you understand. So we cut the beam somewhere, let's say this point, this value of X. Okay, so this is X, and we cut right there, and then we still have the normal, not normal distributed, but triangular distributed load, and because we cut right there, so the load, the triangular load, can be represented by this load, okay, which is the distance is 2/3 of X. 2/3 of X. Okay. So we still have the component at the left hand side, which is the direction force and also the moment, M1. Okay, I forgot about calculating the V1 and M1, the shear, the reaction force at the end of the at the support. So V1 is actually equal to P. So P right here, P is equal to we need to find this area to calculate P. So P is equal to W naught times L. So this length is L. So we will get triangular shape, rectangular shape, and we need to divide by 2 so that we will get the triangular shape, the area, and this area represent the load. Okay, so P is equal to W naught L over 2. So this is equal to V1. Alright, so we know value for V1. Right now we want to calculate M1. So M1, the only, when we consider when we consider the moment about the change color. So we have the beam. So this is the whole beam, not there's no this beam is not cut yet. So this is the P, and then we have the moment. So when we consider the moment, sigma moment is equal to 0. So we are in equilibrium. So actually this direction. So M equal to P time this length, which is 2/3 L. So time 2/3 L. So we know P already, this one. So W naught L over 2 times 2/3 L equal to W naught L square over 3. So if you look right here, the value is similar. Okay, this one. The equation or the equation is similar. So this is correct. Okay, so that is M1. Why M1? Because I want to differentiate between moment at the cross section and moment at the support. Okay, so we know M1 and V1. So right now we can go back to this diagram. Okay, we put it here, and then we know the value of V1 and M1 already. So right now we want to include the shear V and also the moment at the cross section. So this is equation that we want to find V and M across the beam. So we go for the force first. Sigma, in this case, sigma Fy, which is vertical direction, is equal to 0. Okay, the total, the net force in vertical direction is 0. Therefore, what force involved in this diagram is V1 minus P minus V equal to 0. So we may replace with the value, the equation that we have. So V1 is right here, W naught L over 2, and P is, the value of P is similar. Wait. Yeah, similar. But when we do this, it will be cancelled out. I'm sorry. Actually, sorry. So P in this diagram is not similar with P right here, because this is P for the whole length of the beam, but this is I can call it different name. For example, P1. Okay, P1 is different compared to P. P is similar with V1 right here, but P1 is depend on value of X. Okay, so P1 is equal to W X over 2. So this is the equation. W is right here, this value W. Okay, and then X is this length, and over 2. Why? Because this is we want to calculate the area of the triangular right here, triangle right there. Okay, so we just put wx over 2 and v equal to 0. So v is equal to, right now we can replace w with the equation that we calculated before right here. So w is equal to w naught x over L. X over L, x over 2. Okay, and then we can simplify this equation, take out w naught, take out 2L, and what will happen is inside the bracket L square minus x square. So this one is similar with this equation right here, this one, and we make it equation number 1, equation 1. So this is equation for shear along the beam. Now we go to find the equation for moment. Okay, so we need to consider the moment, net moment is equal to 0. So we go back to this diagram and we want to examine what moment involved in this diagram. Okay, let's say this is the pivot. Usually we will make this the cross section to be the pivot. Alright, so we just put everything involved in the diagram. So P1 time the length. What is the length? Length from here, from this point to here. So this is x over 3. X over 3. Okay, P1. And then minus, because this is downward, so it is we consider downward or actually anti-clockwise to be positive. So when we consider the V1, it will be negative. So V1 time V1, not Vi, time the length is x. So minus, and then M1 we need to add because it is anti-clockwise. So M1 and plus M equal to 0. Alright, so now we may replace everything that we have found. P1 is equal to this one. P1 is equal to Wx over 2 and multiply with x over 3 minus V1. V1 is W naught L over 2 times x plus M1. M1 is equal to M1 right here, W naught L square over 3. W naught L square over 3. Okay, and plus M equal to 0, and M is equal to, I can simplify this, we put other component to the another sign, so it will be, this one will be negative, Wx square over 6 and then plus W naught Lx over 2 minus W naught L square over 3. Okay, we can simplify this. Actually the answer is not given right here, but we can reconfirm that. you can try to plot this, and then you will get the curve should be correct. Okay, and maybe we can simplify it further. Since P1 is in terms of W, so we need to replace. Actually, I need to erase. So W is equal to WOX L, and we have X square over 6. Okay, so it should be W naught X cube over 6L. Minus we take out W naught over L. So what will happen is, inside the bracket we will have X cube over 6 plus X L square over 2 minus L cube over 3. Okay, you may try enter. If you want to plot, this is the actually the answer. So this is the curve for V, and this is curve for moment. This is a shear diagram, this is moment diagram. So you can plot this. First of all, let us try this. So let's say X is equal to 0. What will happen is, the answer or the moment will be, this one will be 0, and this one will be 0 as well. So what left is not L square over 3. So you can see that negative. You can see that this one is similar to this one. So that means this equation so far is correct. So what happens if X is equal to L? Is it will be equal to 0? So let's try. Equal to L. So L power of 3 6 plus L power of 3 over 2 minus L power of 3 over 3. So wait. I think we have some problem with the constant. Actually, we are negative right here. Okay, so when we consider the inside of the bracket, it will be equal to 0. Okay, you can calculate that by yourself, and then it is confirmed that this equation is correct, and the shape will be like this. Okay, actually you should find the correct moment equation first, and this should be 2. Sorry. And then you will get this curve. Alright, finish with this example. Now we will go to the example that we haven't learned yet, which is inside the bending deformation of a straight member. Okay. Okay, we have some problem with the diagram right here, and also the unit in this example is in American standard unit, so I think we may skip that. Let's try example 6.12. Let's read that first. Okay, we have so in this subtopic, we will consider the shape of the cross-section area, and now we want to find the stress within the cross-section, and we want to find the maximum. Sometimes we want to find the maximum stress, and maybe some other problem related to this subtopic. So first of all, you need to find the moment or the moment inside this beam, so that you can use the formula right here, to calculate the stress in the member. Okay. So this is the cross section. Okay. Actually, even though this cross section is quite complex, but it's not very difficult. Actually, you can divide this cross section into three, which is if I draw right here, this is the first one, the second one, three shape, and third one. So this is three rectangular shape, and for rectangular shape, we know the how to calculate the I, the moment of inertia. Okay. But before that, we want to calculate the moment inside this beam. So the moment inside that beam it's not very difficult in this case, because there's only one load, and we don't have moment at the end, because this is we have roller and we have pivot, so there is no moment at the ends. There's no moment right here and no moment right here. The reaction moment, there's no reaction moment. So load is applied in distributed behavior. Okay, and this is 5 kilonewton per meter. And of course, the moment this distributed load can be represented by single load, which is at the middle. Okay, why? Because this is not triangular but rectangular distributed load. So what is this value? And also before that, we can write the reaction force. So this V1, this V2, and this we can say P. So P is equal to 5 kilonewton per meter time the total length, which is 6 meter. So we will get 30 kilonewton. Okay, is it correct? So right now, we want to find V1 and V2. So V1 and V2 equal to V2 equal to 15 kilonewton. Right, simple. Okay, and now we want to find the equation for moment. So before that, we may want to calculate the equation for shear. So here V and moment M. So we have V1 only. We don't have moment, reaction moment. So V is equal to we have P1. V is equal to V1 minus P1. Okay, so V1 is equal to 15 kilonewton and P1 is 5 kilonewton per meter time the length of X. So X we can put X right there. Okay, so this is the equation. We don't have to write the unit for simplicity. So this is the first equation. Now we want to find the equation for moment. So we consider the same diagram right here. Okay, so the moment involved in this diagram is again net moment is equal to 0. So we consider the pivot to be at the cross section, at the cut. So V1 X minus P1 X over 2. Okay, and then this is clockwise, this is anti-clockwise, and this is anti-clockwise. So minus M equal to 0. Therefore M is equal to V1 X minus P1 X over 2. Okay, so we replace the value. V1 is we have calculated the V1 right here, 15 kilonewton. 15x minus P1. Do we know P1? Sorry, I think I have made mistake. Wait. Okay, P1. P1 we haven't calculated yet actually. So P1 is actually related to this equation. I can write with different color. So P1 equal to 5 kilonewton as well. This value time X. Okay, so P1 is 5x. So I need to change color again. 5x x over 2. So 15x minus 5x square over 2. Okay, so if we want to check whether this is correct or not, this is equation number 2. You can try to put the value x equal to 3. So let's try that. X equal to 3. We should have a 22.5. M equal to 45 minus 5 times 9 over 2.
45 minus 45 over 2, 22.5. So this is equal to 22.5. So this is similar with this one. Okay, so this equation is correct. Okay, actually you need to find this equation first, and then you can get this curve. But I show you this this trial just to show that my equation is correct. Actually, this equation is not included here, but you can. That's why I do this example, so that you can see how I solve it, how we can solve this problem. So right now we have found the m, and now we can use the formula stress equal to, can I remember or not, my over I. Is it correct? So we have negative, so we can use this equation already. So we need to find I. For I, like I said, we can separate the value of the calculation of I into these three rectangular, and you can see right here how to get the value of I. So we have the formula right here. Okay, first, well, we want to calculate the I, and then we want to the I for each rectangle, and then you want to consider the neutral axis. Okay, for the rectangular with centroid not aligned with the axis, you need to multiply with AD square. So this is the formula, AD square. D is the distance from here to here, from between the two centroid, between the centroid and the neutral axis. This one is also similar, but for the middle rectangle, you don't have to add the AD square, because the center of the area is what we call it, aligned with the neutral axis. How do I know the neutral axis at the middle? Of course, because this is symmetrical, so I know that the neutral axis is at the middle. But in some case, we don't know the neutral axis location, so in that case we need to find the location. So right now I just going to show you how to calculate that. So if you notice right here, we have two right here, these two, okay, and these two is representing these two rectangle, 1 and 2, which is offset from the neutral axis, and this another bracket is for the rectangle at the middle. Okay, so we look at the rectangle at the middle first. So this is the formula, 1/2. We have the formula, if I'm not mistaken. So the formula is right here. This is the formula. I may write down right here. I equal to 1/12 BH cube. So you need to understand what the difference between B and H. So H is the length which is perpendicular to neutral axis, and B is the length parallel to neutral axis. Okay. Wait. So we are right here. Okay. So by using this formula, we can get this equation. 0.02 is actually the thickness, which is this is parallel to the neutral axis end right here, and then 0.3 is the length between from B to yes, the length for the vertical rectangle. So 150 times plus 150 is 0.3 meter. So we powered it with 3. So this is the moment of inertia for the rectangle at the middle only. And for the rectangle, the two rectangle, this one and this one, this is the formula. 1/12 times 0.25. 0.25 is this length, which is parallel to the neutral axis, and 0.02 is the thickness, 20 millimeter or 0.02 meter, and power of 3. And then you need to add with the AD. AD is the area. Area is 0.25 meter times 0.002, which is thickness, and then you need to multiply with D. D is the offset, like I said just now. This D is the offset. So the offset is, if you look at this diagram, not 150 but 150 plus 10, because the thickness is 20, the half of the thickness is 10. 10 plus 150 is equal to 160. So that's why we have 0.16 square. So when you total this up, everything, so this is the moment of inertia for beam with cross-section shape like this. Okay, this is the value. So we got the value for I. I is equal to 301.3 times 10 power of -6 meter power of 4. Okay, and then we want to find, we go back to the determine the absolute maximum bending stress. So we want to find the maximum bending stress. So the farthest location of the cross section from the neutral axis is 170, because 150 plus 150 plus 20 is equal to 170. So C in this formula, why C is the location for maximum. So in this case, Y is equal to C, is equal to 170 millimeter. And have we got all values? Yes. So we just put in the values inside this formula. Okay, and then you can get that the maximum stress is 12.7 megapascal. So this is the answer for this example. Alright, but we haven't finished yet actually. And what we need to do is draw the stress distribution over the cross section at this location. Okay, we need to draw the cross section, the distribution of stress across the cross section. So actually it's quite simple. So stress, we use the formula negative MYI. So what you can do is you can change the value of Y. So from, if you want to draw it, Y equal to 170 millimeter, and then you reduce to 150 millimeter, or if you want to make it maybe 120 millimeter, so minus 5, so 100 maybe 80 millimeter, 40 millimeter. Okay, so when you get the value for stress for each of these, you can plot it, and then you will get this kind of shape. Okay, and notice that the arrow is, since the bending is like this, compression should be the arrow is toward the surface, and for tension the arrow is outward from the surface. Okay, so this is the diagram that we need to draw for this example. Okay, now we go to the next last example before we finish with this subtopic, example 6.13. So I'm going to I just want to emphasize on one thing only. Like I said just now, when the cross section that we used just now is like this, and it is symmetrical, so we know that the neutral exists at the middle. But what happens if the shape of the cross section is like this? Do we know the neutral exists location? No, we don't know. So what we need to do first is we need to find the location of neutral axis, which is y, I don't know what to call it, y prime perhaps. Okay, so how to do this? This is the formula to locate the location of neutral axis. So what you need to do is you need to let's say for this example, you draw the rectangles, okay, and then let me erase this first. You set this is the reference line, so the simplest is this line, which is aligned with the top surface of the beam. Okay, so this is the reference line, and then you may know the centroid for each rectangle. So the centroid for this one is, this is the parallel line, this is the parallel line which is at the middle, and this is parallel line across the centroid of each rectangle. So this is the centroid, this is centroid. So now so we use this formula y a. So what is this y a? This y prime. This is y prime for each shape. So y prime. This is y prime for, let's say this is rectangle A, rectangle B, rectangle C. This is y prime A. This is y prime C, and for y prime B is different, a little different, which is right here, small, according to this reference line, y prime B. Okay, so you need to calculate y prime time area, and then you need to total them all. Okay. So since A and C has similar y prime value and also similar area, so we just multiply with 2 right here. You can see 2 right here. Okay, 0.1 is the length. Wait, 0.1 is the y prime. Okay, y prime, which is, if you look at here, from the end to the middle, which is 0. Let me see. So this length is 200 mm. So y prime is equal to 100 mm. Okay, and then 0.2 is the length, and 0.015 is the thickness. Okay, so that is for both A and C, and this part is for rectangle B. 0.01 is the thickness, if I'm not mistaken. No, 0.01 is the y prime B equal to 0.01 meter. 0.02 is the thickness, and then 0.25 is the length. Length is 250 millimeter. So we get that value, and then divide by total area. So we just add all area and put it at the bottom of the fraction, and then you calculate that, and you will get the y prime for neutral axis. So neutral axis is 59.09 millimeter, which is somewhere around here. Let me draw with red color. So this is the neutral axis. We can put N. Okay. So now we able to find the what we call it, the location of the neutral axis from the reference line. So this is how you find the neutral axis location. Okay. So the rest is the same like the previous example, and you may try it by yourself. So I think that's all for our session tonight. Right now it's tonight. So for today, thank you very much, and